The world around us seems solid, predictable. Objects have definite positions, colors, and speeds. Yet delve into the heart of matter, into the realm of atoms and the particles within them, and a stranger, counterintuitive reality emerges. This is the quantum realm, governed by the laws of quantum physics. Here, certainty dissolves into probability, and the very act of observation can influence the outcome of an experiment. Classical physics, the physics of Newton and Galileo, fails spectacularly at these scales. To understand the behavior of atoms and the forces that bind them, we need a new set of rules: quantum mechanics. This revolutionary theory, developed in the early 20th century, has profoundly changed our understanding of the universe and our place within it. The seeds of quantum physics were sown in the late 19th and early 20th centuries. Physicists, armed with increasingly sophisticated instruments, began to probe the nature of light and matter at their most fundamental levels. What they found challenged the very foundations of classical physics. One of the first hints came from the study of blackbody radiation, the light emitted by heated objects. Classical physics predicted that the intensity of this radiation should increase infinitely as the wavelength of light decreased. This clearly wasn't happening. Instead, experiments showed a peak in intensity, followed by a drop-off at shorter wavelengths. This discrepancy, known as the ultraviolet catastrophe, sent shockwaves through the scientific community. In 1900, Max Planck proposed a radical solution. He suggested that energy, instead of being continuous, was quantized, meaning it could only exist in discrete packets or quanta. This revolutionary idea marked the birth of quantum physics. Further evidence for the quantum nature of the universe came from the study of light. For centuries, scientists had debated the nature of light. Was it a wave, like ripples on a pond, or a stream of particles, like tiny bullets? In the 19th century, experiments seemed to settle the debate in favor of the wave theory. Light exhibited properties like diffraction and interference, phenomena that could only be explained if light behaved as a wave. However, in 1905, Albert Einstein, in his explanation of the photoelectric effect, resurrected the particle theory of light. Einstein showed that light could interact with matter as if it were composed of discrete bundles of energy, which he called photons. This dual nature of light, exhibiting both wave-like and particle-like properties, became known as wave-particle duality, a central concept in quantum mechanics. The early 20th century was a time of great intellectual ferment in physics. The discovery of quantum phenomena sparked heated debates and led to the development of new theoretical frameworks. Two giants of 20th century physics, Albert Einstein and Niels Bohr, were at the forefront of these debates. Bohr, along with Werner Heisenberg and others, developed the Copenhagen interpretation of quantum mechanics. This interpretation embraced the probabilistic nature of quantum phenomena, arguing that at the atomic scale, physical properties like position and momentum do not have definite values until they are measured. Einstein, deeply uncomfortable with this inherent uncertainty, famously remarked, "God does not play dice with the universe." Despite their disagreements, the work of Einstein, Bohr, and other pioneers laid the foundation for our modern understanding of quantum mechanics. One of the most bizarre and intriguing concepts in quantum mechanics is superposition. In the quantum world, particles can exist in multiple states simultaneously. This is not to say that we simply don't know which state a particle is in until we measure it. Rather, the particle exists in a blurry, undefined combination of all possible states at once. This strange concept is often illustrated by the thought experiment known as Schrödinger's cat. Imagine a cat sealed inside a box along with a device that has a 50% chance of releasing a lethal poison. According to quantum mechanics, until we open the box and observe the cat, it exists in a superposition of states, both alive and dead at the same time. While we never observe macroscopic objects like cats in superposition in our everyday lives, the concept has been experimentally verified countless times in the quantum realm. Entanglement, spooky action at a distance. Perhaps the most mind-boggling concept in quantum mechanics is entanglement. This phenomenon occurs when two or more particles become linked, even when separated by vast distances. These entangled particles share a special connection, and the state of one particle instantaneously influences the state of the other, regardless of the distance between them. Einstein famously called entanglement spooky action at a distance. He found the idea that two particles could affect each other instantaneously across vast distances deeply unsettling. However, numerous experiments have confirmed the reality of entanglement, even at distances of hundreds of kilometers. Entanglement has profound implications for our understanding of the nature of reality and has the potential to revolutionize fields like computing and communication. Quantum physics in our everyday lives. While quantum mechanics might seem like a strange and esoteric theory, its principles underpin many technologies we rely on every day. From lasers and transistors to medical imaging and GPS, quantum physics plays a vital role in our modern world. Lasers, for example, exploit the quantum property of stimulated emission to produce highly focused beams of light. Transistors, the building blocks of modern electronics, rely on the quantum behavior of electrons in semiconductors. Magnetic resonance imaging, or MRI, utilizes the quantum properties of atomic nuclei to produce detailed images of the inside of the body. Even the Global Positioning System, or GPS, relies on precise timekeeping made possible by atomic clocks, which exploit the quantum nature of atoms. These are just a few examples of how quantum physics has revolutionized our lives. As our understanding of this strange and wonderful theory deepens, we can expect even more groundbreaking technologies to emerge. The future is quantum, from computing to teleportation. The future of quantum physics is bright with promise. Researchers around the world are working to harness the bizarre and powerful properties of the quantum world to develop new technologies with the potential to revolutionize fields like computing, communication, and medicine. One of the most exciting areas of research is quantum computing. Unlike classical computers, which store information as bits representing 0 or 1, quantum computers utilize qubits, which can exist in a superposition of states, representing both 0 and 1 simultaneously. This allows quantum computers to perform calculations exponentially faster than classical computers for certain types of problems. Another promising area is quantum communication. By exploiting the properties of entangled particles, researchers hope to develop ultra-secure communication networks that are impossible to eavesdrop on. Quantum teleportation, the ability to transfer quantum information instantaneously between distant locations, is another area of active research with mind-boggling implications. These are just a few examples of the exciting possibilities that lie ahead in the realm of quantum physics. As we delve deeper into the quantum world, we can expect even more mind-blowing discoveries and technological breakthroughs. The never-ending quest to understand the universe. Quantum physics has revolutionized our understanding of the universe, revealing a reality far stranger and more wonderful than we could have imagined. It has also led to the development of technologies that have transformed our lives. Yet, despite its successes, quantum mechanics remains a deeply mysterious theory. Many fundamental questions remain unanswered, such as the true nature of wave-particle duality, the meaning of superposition and entanglement, and the relationship between quantum mechanics and gravity. The quest to understand quantum mechanics is a journey into the heart of reality itself. It is a journey that has already yielded profound insights and technological marvels. As we continue to explore the quantum world, we can be sure of one thing: the universe will continue to surprise and amaze us with its elegance, its strangeness, and its endless capacity to challenge our understanding of the cosmos and our place within it.